welcome Joran. His talk is about many body physics with ultra-cold particle disorder.
After a little bit of difficulties, I can start my talk. Does everybody hear me? Yes, good. And first of all, I'm grateful for the invitation to come here. It's a great pleasure. Frankly speaking, I'm a little bit sick. I got cold, and I was going to warm up a little bit here in Taiwan, but it turned out that this does not work. I'm really sorry. Yes. So actually, today I will talk about many body physics with outer-cold atoms in disorder. So here is the outline of my talk, and I will give a lot of, let's say, overview things, and thank you. When I will be presenting my original results, these are the results which are obtained together with Boris Altshuler, Igor Alainer, and San Michel. So, a little bit of a historical note. When we talk about outer-cold atoms in disorder, there is always a question. Why do we have to study outer-cold atoms in disorder? There were very many things which were done for electrons in solids, localization effects, weak localization of transport properties, and so on. Aside from that, there were very many things done with, let's say, microwaves, sound waves, even with light. Why do we have to study outer-cold atoms? What kind of new things we expect? And the answer is twofold. First of all, some years ago, around 2003, 2004, 2005, which is even more than 10 years ago, the study of outer-cold atoms in disorder had been started as a sort of, as an application, yes? And the idea was to make an atom laser. Atom laser is the following. You have a chip, yes? On chip, you make almost one-dimensional atom waveguides, yes? In which you have a strongly correlated beam of atoms, yes? You may focus this correlated beam of atoms on the surface and study the quality of surfaces. So that's what the idea was. But it turns out that on a chip, when you have an atom waveguide, atoms in this waveguide, they feel imperfections of the surface, yes? And therefore the coherence properties of the beam are influenced by these imperfections. And that's how the problem of outer-cold atoms interacting with disordered impurities showed up in this physics. And people started to study this. But very quickly it turned out that there is many more behind this, and that there are fundamental questions which people have to study, which people may study, which people will study. And one of these questions is how the interaction between particles influence Anderson localization. Let me, within my drawing facilities, these are outer-cold particles in disorder. These guys are just my particles, and this is the disorder potential. It really looks disorder. Let's assume that particles are not interacting with each other, yes? Then it's a sort of single particle problem, yes? And the answer to the single particle problem has been given by Anderson in 1958. And the idea of Anderson was very simple, very great. That there is a destructive interference in the scattering of a particle from a random defect, so that the wave function attenuates at large distances exponentially, and the particle, single particle, gets localized in a certain area of space, and a characteristic linear dimension of which is called localization. In this sense, Anderson localization is a completely single particle thing. And there is an old question, how does the interparticle interaction influence localization? And it's a long-standing problem. It's already about 30 years that people know about it. And it was crucial for charge transport in electronic systems, and now it appears in a new light where the so-called bosons now already fermions too. So, what we do is the following. So, what we are going to understand when these experiments with auto-cold atoms have been started, then what was known already? It was known that Anderson localization exists, of course, and it has been obtained by light, follow microwave, sound waves, electrons and solids, and so on. And what is expected? Anderson localization of neutral particles. It's easy to say, but it's not that easy to obtain this experimentally. In the end, what people have done with cold atoms is very simple. It's like the first BC experiments, which got the Nobel Prize in 2001. In here, you have a trapping potential. It's a magnetic trap. Yes, and in these experiments that I'm talking about, it was one-dimensional. Yes, physics. Then you load outer-cold atoms, which form Bose-Einstein condensate. You superimpose a random potential. These are optical speckles. Yes, and then the density of a condensate gets a little bit disturbed by this. Don't be surprised that I say Bose-Einstein condensation in 1D. In 1D, it's a finite size effect. Yes. Then what you do, you switch off the harmonic potential, and then without the disorder, the gas would expand, and that's how people identified the presence of Bose-Einstein condensate in this system in the first experiment. What happens when you switch off the confining potential but still keep the disorder? And the idea was that the disorder, what it can do, it can stop the expansion. And this would be the effect of Anderson localization. And that's what was really happening eventually in the experiment of the group of Elena Spare, or Serre. Now he is in Palazzo, but the experiment has been done when he was still in Orsay. And then what you see experimentally, that the gas is expanding, and then you see stationary tails of the density profile. And the shape of these tails can be explained by using the theory of Anderson localization for non-interacting particles. Because when the gas expands, the density becomes small, the interaction effects are not important. So that's what was experimentally. And this was the first experiment on demonstrating Anderson localization of neutral particles. And you know, this is a very important list. Now there are very many groups studying outer-cold atoms in disorder. Here I mentioned the Asper group, Giovanni Modugno, Massimo Incuscio, Brian DeMarco, Emmanuel Bloch, Gilman, Estinger, and so on. Yes. And people do various types of experiments. Yes. For example, what they studied coherent backscattering of weak localization for particles in two dimensions. Then they started a propagation of, let's say, particles in a two-dimensional disorder, yes, in Zurich. They eventually found a three-dimensional Anderson localization of cold atoms, several experimental groups, and so on. I just tell this briefly. But there is even more important. That what I was telling you about was sort of outer cold atoms in a true disorder system. Yes. Does everybody hear me well in the last rows? Because I have to keep the microphone very close to my mouth. Yes. Which makes my talk complicated, because usually I show things with my hands. Yes. Okay. But aside from making an experiment for atoms in a true disorder, what people have done, they have done experiments in the so-called quasi-periodic one-dimensional potentials, or Aubry-Asbel-Harker model. What this is, you have a lattice, this red, yes, you have atoms in a tip like this, yes, so that they may hop from one side to another. Then you superimpose a shallow lattice with an incommensurate period, yes, and then you get what people call one-dimensional quasi-periodic potential. And to a large extent, this system mimics particles in disorder. In fact, this system is intermediate in between a perfect lattice, which would be, let's say, only red guys, and disordered systems. And the thing is that here are the equations. If J is the hopping amplitude for particles in this primary lattice, and V is the amplitude of this incommensurate lattice, epsilon is the energy of single particle eigenstates, then for V larger than 2J, all single particle states are localized. If it's the other way around, they are all extended. Yes? And then, what people have done in the group of Massimo Inguscio, Giovanni Modugno in Florence, they have done the system experimentally, where you place these two lattices in a harmonic potential. Then you switch off the confinement, and the system either expands if you are for these smaller than 2J extended states, or it just expands a little bit and stays localized if this condition is satisfied. And this has been found experimentally. Now, many more things have been done in this system. Remarkably, if the group of Elena Spe started experiments with rubidium 87, where Feshbach resonances are quite difficult, then these guys in length, they did potassium-39, for example, for which there is a very nice Feshbach resonance. Feshbach resonance means that there is a dependence of the interaction between particles of the magnetic field. You vary the magnetic field, you change the interaction. U is the Hubbard interaction for particles in this system, yes? And then you see that there is a phase transition between the fluid and insulate. I will talk about this later, yes? And they can address this, let's say, phase transition by measuring details of the momentum distribution of particles, fluid insulate transition. So I specially mentioned this because at zero temperature, yes. At zero temperature in 1D, we may use the term sequence. But at a finite temperature, we don't use this term in 1D. So, there were things which were not exactly expected, yes? And I would say that if I consider particles in disorder in one dimension at a finite temperature, it is known that in one dimension there are no finite temperature phase transitions. Yes, you open books on statistical physics and you see this statement. Because what is phase transition? The phase transition is that there appears or disappears long-range order or at least long-range correlations. And in 1D, all correlations decay exponentially due to thermal fluctuations. So what these people have done in 2010, this is Alainer and Altshuler, and this S is in front of you. They have said that there is a non-conventional phase transition between two distinct states in this system. It's an interaction-induced transition between fluid and insulated states. And the result from the experiment, which was also at a finite temperature in this quasi-periodic potential I just showed. So this is not what is exactly explained. And here is something that people call now, already for some years, many-body localization delocalization transition. Yes? And that's what I'm going to speak about now. Actually, there was a very nice paper by Alainer, Altshuler, Basko in 2006, 2007. There were actually several papers, yes, which were published in some annals of physics, some not easily accessible journals. Yes. And then it was just dedicated to study the question how the interaction between particles influences the localization properties. Assume, please, that you are in the localized regime. And then you study the question how different states of two particles, I call them here alpha, beta, hybridize due to the interaction. You should find the probability P over epsilon alpha, where epsilon alpha is the energy of the state alpha, that for a given state alpha there exist states beta alpha prime such that alpha beta and alpha prime beta prime are in resonance. Which means that the matrix element of the interaction induced transition between these states exceeds the energy mismatch. If you are in the localized state, you have a finite size, localization length, therefore you never match the energies exactly. There is always a mismatch. And then the criterion of localization delocalization transition is that this P is of order 1. So the physics is extremely simple. Imagine, please, that you have, now I will have to shout, you have two states, yes, like this. Then, okay, how do these states hybridize with each other if there is an interaction? How do these states hybridize if there is an interaction? Yes. What you have to do, you have to calculate the matrix element of the transition between these states, yes, and compare it with the energy difference. And if the matrix element exceeds the energy difference, then there is a strong hybridization. That's what we know from quantum mechanics. And it's more or less the same here, yes, at least the same physics, yes. And these guys, Basko and Alainer, they have proven in 2007, I think, that then the state becomes extended. It turns out that the matrix element of the interaction is the most significant when the energies of these states are equal to each other pairwise, or almost equal to each other pairwise. Yes, for example, alpha, alpha prime, beta, beta prime. Then the matrix element is this Hubbard constant U multiplied lattice constant multiplied occupation of beta state divided by the localization. In the continuum case, U multiplied A is nothing else than the interaction constant G. And the energy mismatch is nothing else than unity divided by the product of localization length multiplied and hence the states, actually the minimum value multiplied. Here, what is the probability that the matrix element exceeds the mismatch? You have to take the ratio, yes, and then you obtain this value. Then, in order to find P over alpha, you have to make a summation of beta alpha prime, beta prime, and you obtain this interval. gate, U multiplied A, it's a coupling constant G. And then the critical value of the coupling strength is when this is of order 1. So you calculate this integral. That's it. Yes. So again, if I am in the continuum case, it's G critical. You remove A here, and it's G critical. So that's what it is. This is a critical value of the interaction strength, which induces a transition to delocalization from the localized state due to the interaction. That's what has been actually known already for some years, yes? And now what I can do, I can apply this knowledge to various types of control systems. Yes? For example, one-dimensional bosons, if there is no disorder, then we know that this is a very nice fluid phase, classical gas at temperature larger than the temperature of quantum degeneracy, which is density squared divided by the mass. Then in the weakly interacting regime, there is a thermal degenerate gas here, where gamma is the interaction parameter. The ratio of the mean field interaction to the degeneracy temperature should be small. And then there is a quasi-BEC regime, where the correlations are very. But it's a fluid phase. Disordered non-interacting 1D bosons. It's known that in 1D, all single particle states are localized in disorder, under some disorder. So what happens? Oh my God. So I especially ask people in the last rows whether you hear me. I got no answer. Now it turns out that I'm trying to say something and you don't know what I'm doing. If it goes worse, I have a proposal that all people who are sitting in the last rows just come here, Darren. There is a lot of space, and then we easily communicate with each other. So, interacting one-dimensional models and disorders show intermediate behavior. In which sense? For example, now let me assume that I'm in the localized state, 1D. Single particle states are localized by 1. Yes, and then I include the interaction between particles and apply the criterion that I have written over. Dense phase is unit divided by square root of energy. It's given here. And there is a characteristic energy epsilon star at which it becomes constant and then the Belishev tail goes. Epsilon star is proportional to the amplitude of the disorder and the correlation length of the disorder in certain powers. The localization length in 1D is proportional to energy. Then this dependence is can't be given the characteristic disorder energy. Then, for a classical gas, it's known that what is the chemical potential where N is density, lambda thermal wavelength. I apply my criteria, which is actually not mine, but yeah, other guys have written right here, recalling that U multiplied A is G, the coupling constant. And then I get a critical value of the coupling constant, that it will be unity divided by square root of temperature. In the quantum decoherent regime, the chemical potential is proportional to temperature in the square, and I get that it's unity divided by temperature. I can also discuss the quasi-BEC regime, considering the layers of fragmented pieces in the system, and then the critical interaction strength for delocalization. Is temperature independent. What is the most important now? That I can make the phase diagram. Here is the amplitude of the disorder, here is temperature, here is the light, which separates the insulator regime from the fluid regime. Don't pay attention that here it's red and here is blue. No difference between blue and red. Just why I did that? It's interesting because here it's quasi-BEC regime where the result is temperature independent from the critical can also make a dependence of the critical interaction strength on temperature. And that's like that. At very low temperatures, it's temperature independent, and then it starts to go down with increasing temperature. And we understand that. You increase temperature, yes, and then you understand that the system becomes hotter, and it's easier to induce delocalization in the hot system. Yes, more or less it's like that. Yes. So that's what the result is, and it's awaiting for the experimental realization. One of the difficulties in many experiments, especially in 1D, I will tell later about that, is to control the temperature. What I was telling you is the so-called weakly interacting regime for bosons. But it is known that in one dimension people have also produced the so-called strongly interacting regime. Strongly interacting regime is the regime where this parameter gamma, it's called gamma, is much larger than 1. Then, what one can do, one can use mapping of strongly interacting bosons repulsively onto weakly attractively interacting fermions. It means that it is well known that the bosonic system described by this Hamiltonian, Lieb-Liniger Hamiltonian kinetic energy interaction, G is the interaction node, maps onto fermions with this Hamiltonian. This interaction is momentum dependent, yes, strictly speaking. And the dimensionless coupling constant is uniquely divided by my gamma. Gamma is this one. If I consider weak disorder, where the characteristic disorder energy is much smaller than the temperature of quantum degeneracy, or Fermi temperature for these fermions, yes? Then, for fermions, it is more or less known and easy to obtain the transition temperature from insulated to fluid, which will be the characteristic level spacing divided by this parameter lambda C is a order 1. And this level spacing business is unit divided by the characteristic transport time, which I can work out taking into account how the interaction between 1D fermions renormalizes the disorder. This has been done already. And then for DC, I get a dependence that this is just d gamma divided by logarithm gamma in the power of gamma divided by gamma 1 is A. And then you may check that the transition temperature vanishes when this gamma becomes approximately A, which is consistent with the old Giamatti-Schultz result that when the Lagrange parameter in 1D is 3½ this is gamma 0, 7.9, then any infinitesimally small disorder leads to localization. For large temperatures, we can just use the single particle picture and obtain this result. D is the dimension of disorder. So, then, what I'm going to show you is, this is how the dimensionless disorder and this temperature and this is the line separating insulated and fluid. Right? Here you have the dimensionless, here in this graph, this is small gamma, then you approach gamma equals 1. Here you have it for large gamma, yes? And if for example, you assume that temperature is tending to 0, you may draw a phase diagram in terms of dimensionless disorder and gamma, the interaction strength. You know that at very small interactions, you have insulated. You increase the interaction, you get to the superfluid phase, and then further increase of the interaction, you again become insulated. there is a re-entrance to the insulator state. And this picture, at zero temperature, it is possible to extract it from the work of Shlyapnikov and Schultz. And because Shlyapnikov and Schultz, they are here, large interactions, but also from the work that people have done for superfluid insulator transition at zero temperature. There was a lot of numerical work and so on. What actually we have done, we have shown that this behavior, re-entrance to the insulator state with increasing the interaction constant, that this behavior takes place at any finite temperature. This is zero temperature. You increase temperature, you will go to a classical gas, and you get back to this picture. Yes. That's what here. This is shown in terms of temperature and gamma. Yes. Insulator, fluid, insulator. Yes. Now, what I would like to do is to say that I already spent quite some time to explain about one-dimensional bosons in disorder. Then our beloved chairman can tell me how much time do I still have. 13? Great. Then I would like to say a few words about the work which has been done for interacting particles in the Andreev-Aubry-Harper lattice in 1D quasi-periodic potential. You know that for this system a lot of interesting work has been done in the single particle case.
I want to make sure that you just mentioned that there's no experiment to verify the theory so far about the finite temperature transition.
Finite temperature phase transition.
Not yet.
Not quite. Well, the experiment has been done for, let's say, bosons in 1D quasi-periodic potential. I already mentioned this experiment,
Yes.
and I will tell later about it.
Okay. So that's
Yes. Here, in this system, atoms in quasi-periodic potentials, a lot of single particle physics has been done. For example, it has been obtained that when V is close to 2J, the localization length is much larger than the lattice constant. Yes? The density of states consists of clusters, and the width of the cluster increases with energy. What it means is that the density of states is the largest here, then it goes down here, goes down here, goes down here, and so on. Now, after people have done a lot of interesting single particle work, yes, the tens of papers have been published, yes, and what we can do, we can assume that particles interact with each other. There is this Hubbard type of interaction, so that there is an interaction constant U when particles get one and the same lattice side. Now, for simplicity, I will assume that the ratio of periods of my initial primary lattice to the period of the shallow lattice is small. So this period is much smaller than this. Just
Right, question. For your argument seemed originally it sounded like you can assume random energy positions, but clearly they have a lot of correlations.
yes.
So does it still, can you still use the same arguments for such correlated spectrum?
The thing is, yes, we do. And I got this question from your friend and collaborator, Yehud Altman, who always asks these questions. But the answer to this nasty question is, in order to test that this many-body localization, delocalization transition originally developed for the solid system works. People have done Diamarchi and check. Yes, it works.
There is no understanding. The emoji is like a black box. It's the way to understand why example goes through, because maybe we have these giant gaps in the study.
The understanding why it works is present because what people have said already a long time ago, that this Andrea Aubry lattice, it mimics the disorder, and on a long distance scale the system looks more or less like a disordered system. Yes, because two incommensurate lattices, they produce a la disordered system. Yes, if you look at a long distance.
I'll ask you.
Yes. And the details of the spectrum, they are more or less like that. Yes. So, then, what happens is the following. Let us, if the number of clusters in this case is such, it's unit divided by the ratio of the periods. So, if it is and the width of a cluster grows exponentially with energy, then if the number of clusters is smaller than the localization length in units of the lattice constant, yes, then this guy, localization length divided by the number of clusters, is the number of states of a given cluster participating in the localization delocalization transition. If my temperature is much smaller than the width of the energy spectrum, which is 8J, then the delocalization criterion is written like that, where gamma 0 is the width of the lowest energy cluster, this is the density of states, localization length, and so on. What is important here, please pay attention to that, density of states in the square. The occupation number of particle states, it's